Now, in the last video, we saw the construction of the bounded linear operator between two Banach space. And in this video, we want to show that all such bounded operator under the operator norm is actually a Banach space itself. All right, so this is probably the third time we prove something is a Banach space. Okay, so you will probably notice the proof is very similar to what we did before. Okay, so let's start. Well, before we prove is a Banach space, we actually haven't showed this B of V to W is a vector space. Okay, so let's show that first. So to show it's a vector space is fairly simple. So let's start from any S and T inside this B from V to W. And let's take two scalars, let's say A and B inside R. Again, all the vector space are real valued, well, over the reals. So let's take our scalar, real scalar. So now I need to consider what happens to AS plus B of t. Okay, so this is what we want to show. We need to show this is again bounded. So let's just take any vector v inside V where the length is less than or equal to 1, or the norm is less than or equal to 1. So let's test it on this V. All right, so this is really simple. So you consider that, and everything is linear. So you, by definition, this linear combination of this operator is just A times S of V plus B times T of V. Okay, and you can use the triangle inequality, break it into two, and you realize A and B they're scalars, so you can pull them out. So you pull out the A, that's A times the norm of S of V, and you plus the norm of the absolute value of B times the norm of T of V. Okay. And because S and T, they are bounded, so S of V, T of V, when you evaluate on some vector norm less than or equal to 1, they're bounded about by their own operator norm. So this is bounded about by A times S plus B times the operator norm of T. The point is S and T, they are bounded, so when you do this linear combination, it's going to be finite, okay? So because the left-hand side, this value on the left-hand side is bounded above by this constant on the right-hand side, it doesn't depend on which vector you pick. Okay, as long as your vector norm is less than or equal to 1, you're always bounded about by this number. So you can show that this is essentially saying the norm of AS plus BT that's actually also bounded above by the same thing. Okay, so in particular, it's going to be less than infinity. Okay, so that just shows AS plus BT is inside the B of V to W as well. So we have a linear structure on these bounded operators. All right, so now let's prove it's actually a complete vector space. Well, to show that this norm is, well, we first of all need to show this is actually a norm. Okay, so let me actually show that first. Okay, so let's show why this is a norm. Well, first of all, to check it's a norm, the norm of 0 is, well, the 0 maps, just map everything to 0, so that's going to be 0, that's clear. And if you have the operator norm t is equal to 0, then from last time we saw that t of v for any v is bounded about by its operator norm. Okay, that's in W. Multiply the norm of v, that's in V. And because the operator norm is equal to 0, so this is going to be 0. So in other words, t of v is going to be 0 for all v. While here v can be anything, so t is just a 0 map. Okay, so t is going to be 0. Okay, so the operator norm is equal to 0 even only if you're just evaluating the 0 operator. And you need to prove the triangle inequality. Well, let's prove triangle inequality. So you have S plus T. Okay, so the norm of S plus T, that's the supremum of all the, you evaluate the S plus T evaluates on some V. Okay, that's just by definition. So here you take any V with this norm less than or equal to 1. Okay. So because you can write by the triangle inequality, you break it into two parts. So this is just the S of V, the norm of SV, plus the norm of TV. Okay. So here again, V is the norm is less than or equal to 1. Okay. And if you think about this, for any V, this S of V, that's going to be less than or equals to the operator norm of S. and the T of V is going to be less than or equal to the operator norm of T. So you're taking a supremum over a bunch of things, and the value, each of these values is bounded above by this constant. Okay, so this whole supremum is also bounded above by this constant, okay, S plus T, okay? So this just shows the triangle inequality. And finally, if you evaluate AS, the operator norm of that, that's just going to be equals to A times the operator norm of S. That's just, you write out the definition, and it's just one step. I'll leave it as an exercise. All right, so now I have, that's a norm. And finally, let's show that it's complete. Okay, so let's show BVW with this norm. We have it's a vector space, we have it's a norm. Let's show it's complete. Okay. So like I said, this is probably the third time you see we prove something is complete in this course. So try to compare the proof I'm giving out to what you did or what you see in the L1 or LP or on your assignment L infinity. Okay. So here's the proof. So if you recall what happens when we prove L1 is complete, for example, okay, so first of all, we need to define a pointwise limit. Okay, so we want to define some pointwise limit. Well, the starting point, because we're in some vector space, we can always start with some operator Tn where the norm is less than or equal to 2 to the negative n. Okay, and so we want to show that there's some n going from 1 to infinity of these Tn that exist in the in B of VW. Okay, so not only it exists, it's actually the norm limit of the partial sums. Okay, so that's what we kind of the setup we had before. So the first step is always we define a pointwise limit. Okay, so in this case, I need to define how can I define this infinite sum evaluate on some vector. So let's take any vector V inside V. And if I consider the following, so if I consider the summation of the Tn of V, okay, so here n going from 1 to infinity, well, each of these Tn of V from the remark I had in the last video is bounded above by the operator norm of T times the length of V, okay? So here, this V is going to be fixed, okay? So I'm just take any V for now, okay? So this is going to be a constant that's now dependent on n, and I'm missing a Tn here, all right? So this is essentially, I can move the V outside, okay? And I evaluate the summation of the norm of Tn, okay? And greater than or equal to 1. And by our choice, the norm of these Tn are bounded above by 2 to the negative n. So I have the norm of V times the summation of 2 to the negative n. And you know this is just equals to 1. Okay, but the point is this is going to be less than or equals to infinity. Okay, this is bounded. Okay, and it's because it's bounded. Okay, so you have a sequence of vectors Tn of V, and their sum is bounded. So they're absolute convergent. And in the Banach space, when you have their norm converges, well, then they have to converge as well. Okay, so because the space W is a Banach space, and if you consider the summation of Tn of V, so n going from 1 to k, so here k going from 1 to infinity, so this is a sequence of vector in this Banach space. This is a Cauchy sequence, okay? Because it's W is complete, so this converges, and I just denote it by the infinite sum, okay? So let's define S of V to be the limit, okay? So I use the notation n going from 1 to infinity of the Tn of V. That actually exists inside this Banach space W, okay? Because I have these partial sum is a Cauchy sequence, so it has a limit. Okay, let's just define it as the limit. So now I defined a pointwise map, okay? So this S is, I know how to define it on every single point, okay? Compare it with the proof of the L1 is complete, we're basically defined a pointwise limit, okay? So now the second step, I need to show that, recall what we did in the L1, we define a pointwise limit. Well, we need to show this pointwise limit is inside the normed vector space. So here's what we do as well. So that's the second step. let's show that S is actually inside B of V to W. Okay, I'm not converging to some map that's crazy. All right, so to show that, I need to show two things. So first of all, S needs to be linear. Okay, so if I evaluate S of some A times V1 plus B times V2, where A, B are just scalars. So by definition, so this is just the limit and goes to infinity of these partial sum. Maybe let's say K goes to infinity of the K partial sum. Okay, so Tn of the vector. This is the definition of this S. Okay, so this partial sum converges because it's Cauchy. We proved it just now. But each of these Tn, they are linear. So I can break each of these Tn of AV1 plus BV2 into two parts. Okay, so this is the summation n going from 1 to k of Tn of V1, and I multiply by A plus B times Tn of V2. Okay. And it's fairly clear I'm only taking finite sum, so I can break it into two parts. So I can take the limit of the summation Tn of V1 first, and I break it into the limit of the summation of B times Tn of V2. And now I take the limit, then by definition, this is just A times, well, you can move the A and B outside as well. So this is just A of SV1 plus B times SV2. Okay, so that's fairly clear. So S is going to be linear. And next, I need to show S is going to be bounded. Okay, so that's the second thing. So now let's again fix a vector V where the norm of V is less than or equal to 1, and let's see what happens to S of V. Okay, so let's evaluate S of V inside the W norm. Okay, so by definition, what it is, well, this is essentially just, again, the limit of the partial sums. Okay, so summation n going from 1 to k of the Tn of V. Okay, and we know how to evaluate these because I have a finite partial sum. This is by the triangle inequality. I can move the summation outside and have a less than or equals to. So this is Tn of V. And each of these Tn of V, because V here is some norm less than or equal to 1, this is bounded by the norm of Tn, which is again bounded by 2 to the negative n. So I have this is bounded above by the summation of n going from 1 to infinity of 2 to the negative n. And again, this is a constant less than infinity, okay? So this is a constant that doesn't depend on V, so what I have is as the operator norm is bounded above by the same constant, okay? So actually, if you evaluate, that's just equal to 1, so S is bounded above by 1, okay? So in particular, it's less than infinity. Okay, so I basically now show that as a linear, and the operator norm is less than infinity, so S is a bounded linear operator between V and W, okay? So this part is done, and again, if you compare with the L1 proof, it's basically showing the pointwise limit is an L1 function. And the last step, I need to show this S is the limit in the correct norm, okay? I only have a pointwise convergence. Now I need to show it has a norm convergence. Okay, this is basically compare the L1 is complete. I need to show the pointwise limit is the L1 norm limit of the sequence of function. Okay. All right. So what I do is I compute the difference between S and I want to show is the limit of the partial sum. So let's take the difference of the partial sum of these Tn. So I can evaluate to compute this operator norm. Let's just evaluate on some vector V where V is the norm is less than or equal to 1. Okay, so here again, norm of V is less than or equal to 1. Okay, I'm evaluate inside as a norm in W. All right, so one thing you can convince yourself, well, this is the S is basically the summation n greater than or equal to 1, and you take away the kth partial sum. So that's going to be equals to the limit of the partial sums where you start with k plus 1 to some, say, n. Okay, n goes to infinity here. And you have a Tn of V, okay? But in any case, you can do the same trick using the triangle inequality, and you bound these Tn of V again, so I'm not going to write all the details. This is bounded above by the series. So you sum when k going from k plus 1 to infinity, and you evaluate the norm of Tn, which is bounded above by 2 to the negative n, and you know this infinite sum is 2 to the negative k, so that goes to 0 as k goes to infinity. Okay, so this essentially just shows that the s minus the summation of these Tn, these partial sums of Tn, okay, the operator norm is going to 0 as k goes to infinity. Okay, that's just another way of showing these partial sum converge to s in this norm. Okay, so this is the last piece. Now we finish the proof that this is complete. And I just want to remark one thing. If you go over the proof, you may realize we never use V as a Banach space. Okay, so V don't need to be a Banach space. Okay, it doesn't have to be complete. In other words, it doesn't have to be a Banach space. As long as you have V is a normal vector space, then you're okay. Okay, the same proof goes through. We only use W is a complete vector space. All right, so now we finish this definition of bounded operator, and I'm not going to do too many bounded operator. There's only one thing we need to know in this course, basically is the dual space. So the dual space is probably the simplest one. So essentially you do the following. So let's let V be a, again in this course, we only care about real vector space. So let's say real. Okay, so V is a real Banach space. Then the dual space, okay, so the dual space is the following. So I use the notation V of star. That's essentially all the bounded operator from, well, V is a Banach space, and I move it to R, okay, the real line, you just equip it with the usual distance, okay, the absolute value of their difference, okay. So this is called the dual space, okay. This is the dual space of this Banach space V. And by the remark, actually, you don't need this V to be Banach space. As long as V is a norm, the vector space, you also have a dual space. Okay, but we're going to look at Banach space most of the time. So let's just assume it's a real Banach space for now. And this element, we have some special name. Let's don't call them bounded linear operator because the range is inside R. So a map inside this dual space, let's give it a special name. Okay, that's called a linear functional. Okay, so this is linear functional. Okay, so this is exactly where the functional analysis come from. Okay, you're analyzing these functionals. And sometimes, again, you don't need to specify linear. Everything is linear. So sometimes we just call phi a functional.